All right, guys, we just want to finish up the alcohols chapter. We've already talked about quite a few reactions of alcohols, and we don't have that many to go. So we want to get into finishing up the substitution reactions of alcohols and then think about oxidation of alcohols. There's a couple of mechanisms that we have to go over as well in that substitution bit to kind of finish up some of those reactions we've already introduced. So I'll talk about those in a second. After that, I mentioned that we're going to move into oxidation of alcohols, and there's a few oxidizing reagents. And this is one of those situations, like I said before, with reducing agents, that you want to kind of keep an eye on the actual reagent itself, because ultimately these reagents are going to come up again later on down the road, and they're going to do similar chemistry. In other words, they're going to do oxidations. And so again, this will be pretty short to get you ready to go the next time we meet. We're going to do some problem solving. And so I hope you have a great weekend and get this knocked out before we meet again. So let's go ahead and get into it. Let me start up my whiteboard and we'll go from there. All right. So let me get this screen shared. Okay, and so we started off, this is essentially exactly where we left off with some of the reactions that we talked about. I mentioned that we needed to know the reaction mechanism for SOCl2. We also need to know the reaction mechanism for PBr2, PBr3. Let me correct that. And I wanted to start off with just a couple of notes about all of these mechanisms. They have an analogous stereochemical outcome as if you were to turn it into a tosylate first and then react it with some other nucleophile in order to, well, the nucleophile is here, to do a substitution reaction. Remember, the whole point of reacting it with the tosylate is to make it is that OH is a bad leaving group, and we want to turn it into a good leaving group. And so the first reaction with tosylate creates the tosylate ester, and then that is a good leaving group, in which case we can then do nucleophilic attack with the chloride. Now, what happens if we do this at a secondary carbon? And if that secondary carbon involves a chiral center? Well, the first step of the formation of the tosylate group doesn't do anything to the stereochemistry. But remember that since the second part of the reaction is SN2, there is a conversion in this, an inversion in the stereocenter. And this is true for essentially all of these reactions. And so just keep that in mind as you move forward. Be sure to check out the review section at the end of the chapter that lists all the different reactions, because in that section, they do a really good job of making sure that you see that all of the stereocenters are inverted in these substitution reactions. If you keep in mind that they're substitution reactions at their heart, SN2, then you should know that from Orgo 1, that all of those reactions involve an inversion in stereochemistry, and so that's going to be the stereochemical outcome. So we did the reaction of SOCl2 and pyridine, HCl and zinc chloride, and then PBr3 as well to do these substitution reactions. All PBr3 will add on a bromine, SOCl2 and pyridine will add on chlorine, HCl, and zinc chloride will add on a chlorine, and then tosylate chloride and pyridine will add a chlorine. So they're very straightforward ways to change OH groups into halogens. And remember, then once you have a halogen on there, you can do all sorts of different reactions, primarily of which it would be elimination to form alkenes. Okay, so let's take a look at the mechanism for the SOCl2 formation. And one of the things that I want you guys to remember is that when you're thinking about what happens in mechanisms, think about what kind of chemistry is possible based on the relative charges of the relative polarities of the different things involved. What we're going to do is think about the electrons on the OH being nucleophilic and the sulfur itself being electrophilic. And so if you think about the oxygen that's double bound to the sulfur as being more electronegative than the sulfur, then that leaves the sulfur with a slightly positive character. And that should give you the first indication that you're going to attract the lone pairs of electrons onto to the sulfur. And so that's going to form this interesting species like this. It's not actually tetrahedral because remember, I'm not showing the lone pair on the sulfur, but it's there. There is a lone pair here. It's still slightly positively charged because of the electronegativity difference, but there is a lone pair there, so it's not quite tetrahedral in this intermediate. Now what's going to happen is the double bond is going to reform, and at the same time it's kicking off a chloride. We're going to use that chloride later because what we found now is what we've created is a good leaving group. And we're getting close to creating a good leaving group anyway. Now this is where the pyridine comes in. Remember, pyridine is an aromatic base. It's aromatic both in its conjugate acid and the base form. It's going to do proton transfer. Now we've created a good leaving group. Okay, so this structure here is a good leaving group. And so now that chlorine that we had, or the chloride that we had around here before, is now able to do nucleophilic attack, kick off this group here, and that's where I get my products. So I get forgot to narrow. It does kick off a chlorine to form chloride in solution, but then the SO2 is a gas. So there you have it. Now, the mechanism for PBr3 is similar, but not quite as complicated. So if we take this reaction, and I'm going to move it over here just in the corner. Hopefully it's not completely invisible. Maybe we can see some of the similarities between it and the PBr3 reaction. We've got phosphorus tribromide. And I'm going to actually just move it a little bit so that it's just a little bit more conveniently located. And we're going to get the same sort of nucleophilic attack to start off the reaction. Okay. Messed this up completely. It does kick off a bromine in the process. And we're left with that. And now the bromide that we kicked off. Let's try that again. All right. So that one's a little bit more takes one less step. Let's see, 1, 2 versus 1, 2. It takes 2 less steps, but it is essentially the same thing. Nucleophilic attack followed by SN2 reaction, nucleophilic attack, loss of a leaving group. If you look up here in the left-hand corner, you get nucleophilic attack here. Then there's loss of a leaving group. Then there's proton transfer, then there's SN2. And so there is 2 extra steps, but remember they both involve nucleophilic attack and the SN2 step. And remember that SN2 step is what's going to remind you that at the end of the day, there's going to be an inversion in the stereochemistry if there is one to be had. Okay, and so that's really it when it comes to substitution reactions, but you have like several different ways in order to add on chlorines, and you got one good way to add on a bromine or do a substitution reaction where you're substituting OH with bromine or chlorine. So now it's time to move on to oxidation, and we're going to talk about several different oxidizing agents, one of which is strong and the others of which are not as strong. And I'm not going to call them weak. I'm just going to say not as strong. And so let's talk about the strong oxidizing agent first. And that one is going to be ultimately chromic acid. And chromic acid is, it looks like this, HOCr, double bond O, double bond O, OH. It looks like this. When you have sodium, there's a couple of different ways to make it, and the way that I'm going to show it in this course is I'm going to have Na2Cr2O7 with H2SO4 and water, and those things together in solution will create chromic acid. These are the reagents that you'll see, but this is the thing that's doing the chemistry. And so let's take a look. What if I take an alcohol and I react it with chromic acid? And so this is a reaction that you should know. And it's going to be Na2Cr2O7, H2SO4, and water. What it's going to do is it's going to oxidize that alcohol. Now, I said that that one of them was strong and one of them was not as strong. And I mentioned that the chromic acid, the sodium dichromate, is the stronger of the oxidizing agents. In fact, it's so strong that if the alcohol is in a primary position, it will oxidize it as far as it will oxidize that carbon as far as it can go in as far as adding bonds to oxygen. So notice in the first reaction, the OH group is in a secondary position, and so it's not going to break any carbon-carbon bonds. So the most number of bonds that that particular carbon can have is 2 bonds to an oxygen, and so it forms a ketone. If it's in, so this is a secondary carbon or secondary alcohol. If the oxygen is in a primary position, then this carbon can have 3 total bonds to oxygen. And so that makes it, this reaction results in a carboxylic acid. And so if you remember that sodium dichromate and ultimately chromic acid will be the common strong oxidizing agent that we deal with throughout the rest of the course. So you want to keep that in mind, that the chromic acid or the sodium dichromate with sulfuric acid, that's the strong oxidizing agent. It will oxidize a carbon as far as it can go without breaking any carbon-carbon bonds. Okay, so let's take a look at the other. So this is a reaction that you should know. And let's take a look at, put this one in the corner. Okay, let's take a look at the the oxidizing agents that aren't as strong. There's a reagent called pyridinium chlorochromate. It's abbreviated PCC. It's a pyridine. It's a pyridine that has a proton attached to it. Remember, it's aromatic in both its basic form and its conjugate acid. So there's its conjugate acid. And then it's associated with CrO3Cl, which is a negative thing. So it's a salt. So this is what PCC is. And it's an oxidizing agent as well, but it's not quite as strong as sodium dichromate and chromic acid. Now, there is a mechanism that's listed for the Swern oxidation that we're going to talk about here in just a second. The mechanism for PCC is also listed, or excuse me, is not listed. But we're not going to actually require that you know it for this particular course, and so I'm not including it in this video. But if we were to take a look at a reaction for PCC, and we do the same reaction with a secondary alcohol in the presence of CH2Cl2, then we oxidize that carbon again to a ketone. Now, a different result happens if it is a primary versus a secondary carbon. So it's a different result in the sense that compared to chromic acid. So chromic acid is the strong oxidizing agent. PCC is less strong. So it doesn't oxidize all the way to a carboxylic acid. It stops at the aldehyde. And so this is a big difference because in synthesis, you're going to want to be able to create aldehydes versus carboxylic acids. And so you're going to have to make the right choice of oxidizing agent. And so I want to just reiterate that if you're getting to the point where you're recognizing a particular reagent or a particular reaction as having undergone an oxidation, then what you want to be able to do is then say, what kind of oxidation was it? Did it oxidize the carbon fully, or did it stop at the aldehyde? And if it stopped at the aldehyde, then you have to use one of the less strong oxidizing agents. Okay, and so let's talk about the Swern oxidation. This is one that has a mechanism listed in the book. It's more along the lines of, in strength, of PCC. And so it oxidizes as well, secondary carbons into ketones, and it oxidizes primary carbons into aldehydes. Okay. There's one last oxidizing agent that I want you guys to be familiar with. That's DMP. That's desmartin pyridine. Let me make sure I said pyridine. we have lots and lots and lots of abbreviations in organic chemistry. So it's DMP, CH2Cl2, oxidizing secondary alcohols to ketones, but again, it's more along or more properly aligned with PCC when it comes to its strength. And so it does not oxidize primary alcohols fully. It leaves you with the aldehyde. And so at the end of the day, these are the first introductions to some oxidizing agents. Certainly PCC with pyridine, PCC in the presence of CH2Cl2, along with sodium dichromate and sulfuric acid to make chromic acid, are going to be common oxidizing agents. Certainly, depending on which videos you watch or whose lectures you look at on the internet, you may even see chromic acid as the reagent listed rather than sodium dichromate. In this class, we're going to talk about it in terms of sodium dichromate. So just be aware that if you're out there in the internet and you're looking at some of these other reactions, that you remember that it's chromic acid ultimately that's created and is what is doing the oxidation. We also learned about the Swern oxidation with DMSO and SOCl2 in the presence of, then treated with a base like triethylamine. And we learned about desmartin pyridine, DMP, in the presence of CH2Cl2. They're all three, PCC, Swern oxidation, and DMP. They're all less strong than chromic acid and will not fully oxidize a primary alcohol into a carboxylic acid. It only oxidizes the primary alcohol into a aldehyde. So at the end of the day, that's really it for the chapter. So I'm going to leave it there. And what we're going to do when we come back is we're going to, when we get together again, we're going to discuss the synthesis strategies that we use for alcohols, and we'll do some practice, okay? And so that's really where we're going next, because after that, we want to move into thiols and ethers, and that's going to be another chapter that's going to involve some of these similar reactions, especially SN2. So I'm going to leave it off of there. I'm going to post this up on Blackboard, and I'll see you guys soon.